I'd like to introduce Arun Majumdar is the J. Precourt Professor at Stanford in Material Science. It's okay, guys, that he's at Stanford. It's okay, he went to Cal. More importantly than the whole Stanford thing, he was appointed as the first director of the Advanced Research Projects Agency Energy, which is the program that makes energy moonshot everything possible in the Department of Energy. To me, in a lot of ways, it seems like ARPA-E is the grown-up version of Nuclear Innovation Bootcamp if they did nuclear things, which they will. You good to go?
Sure.
All right, I'm so happy and excited to welcome Professor Arun Majumdar to the stage. Thank you.
Well, thank you for inviting a Cal graduate to Cal. In fact, they have a long history, not just as a student, but as a faculty. I got married out here. My wife is a Cal graduate, but I'm at Stanford right now. It's delightful to listen to all the teams that we're presenting, and I want to thank Rachel for putting this together, bringing the next generation and giving an offering an education which is beyond just technical. And I was just been looking at your program, and I think that holistic view of things is so important in the days that we're living in today. And I'm sure you're breathing a sigh of relief now that after 2 weeks it is now coming to a conclusion. And I suspect the only reason you're here on a Friday evening is because there's a reception at the end of this. So, thank you. Can you hear me properly? Great. I thought I'll give you my perspective looking at the energy industry. I'm not going to tell you too much about nuclear. You guys have already heard about it. You had 2 weeks of that. But how does nuclear fit into the larger context of energy? And I thought I'll give you my impression of looking at it for more than probably a couple of decades of this, but more intensely over the last decade. So I call it navigating the turbulence, because those of you who have, how many people have taken turbulence classes? Well, Pierre, of course, you and I did it together, I think. But you have certainly felt your turbulence, and it's a bumpy ride. And I believe we are in a bumpy ride for the next couple of decades, which, by the way, is an amazing opportunity. So the first thing I want to invoke is another Cal graduate who wrote a very famous book, and I want to ask you, who has read the book written by this other Cal graduate, Andy Grove? Only the Paranoid Survive. If you have not read it, it is worth reading. And he describes in that a world that he went through at Intel, when Intel was going almost under in the 1980s. When the fundamentals of this business changed. And he called it a strategic inflection point, where there's an inflection point in a strategy, in this case, a business. It could be an industry, it could be a country, it could be the world. And the idea is that the inflection point in strategy means that the strategy that one had before doesn't apply anymore. The fundamentals shift. And so you can't look at past data. A lot of people say, oh, let's look at data. The past data is of no use, of little use, because it was for the previous world. And if the fundamentals have changed, you got to think differently. And not only you got to think differently, you got to try some experiments. And the strategic inflection point may seem very close in the beginning, but how you adopt the new fundamentals can get you at two different places, okay? And I think the energy world is going through one of these strategic inflection points worldwide. Why is it doing that? There are three drivers for this, and I call this the 3D effect. 1D is decarbonization. This is the Paris Agreement. I mean, it took 21 meetings, believe it or not, to agree that, to acknowledge that there's a problem. And that first D is decarbonization, and regardless of the fluctuations, the political fluctuations, which is almost seems like the Keeling curve, right? The fluctuations, but there's a trend. And that vector is pointing in the direction to decarbonize the energy system or economies. And that is happening through various means. It is the largest industry in the world. It is roughly $10 trillion a year. The second D is digitization. And this is the word that we saw a little bit, we just heard about it. But this digitization is you could say it's a spectrum starting from the 1700s of automation. And this is another version of automation that is coming, and that is going deeply into the energy world, whether it's oil and gas, whether it's transportation. The transportation ones we see because we use Uber and many things, which is, I think, just the start. There's much more coming, but it's in the electricity world as well. And the third one is diversification. People are diversifying. I mean, transportation used to be only, oil and internal combustion engine. That is shifting, and that is shifting to the point that it is there are much more consumer choices. There are many more choices for electricity generation, and that is not only a good thing for the consumers in terms of consumer choice, it is a tremendous thing for national security. And when you're talking about energy, you got three securities that you have to take care of. One is the economic security, the second is the environmental security, and the third is national security. You can't ignore that. And so this is the realm we are in. And after 100 years of enormous success of the industry that has led to economic growth, this is shifting. And if you talk to the people, let's say in the oil and gas industry, which I do a lot, to find out what are they thinking about. And you find that you go to these global industries, you go to the shareholder meetings, and you'll find that half the time they're trying to answer the question when the shareholder is asking, what are you going to do about decarbonization? What are you going to do about climate change? And this is going on as we speak. So they're under tremendous pressure, and the whole business is based on carbon, and then suddenly they've been asked, how do you decarbonize? This is fundamental shift that's going on, and this is going on globally. So these are the changes that are happening, and yet we have some challenges. This is, you may have seen this is where the people live. This is where electricity is used, which is a proxy of economic growth, and you see a mismatch. And there are three grand challenges that we have. How do we continue our economic growth while we reduce our greenhouse gas emissions? So you decouple the two. We have sort of decoupled in the United States, but many parts of the world have not yet decoupled. How do we provide access to affordable modern energy to every human being in the world? That should be a human right in the 21st century. And then number three, how do we make our energy system reliable, resilient, adaptable, secure against various threats? And climate is one, cyber is I don't have to even tell you that, cyber is a big threat. So you got these three drivers of change, which are sort of pulling the rug out of people's understanding. And you got these three grand challenges. And the big paramount question is, how do we create pathways to address the grand energy challenges and navigate this 3D landscape? This is the challenge. And people who are sitting whether in the oil and gas or transportation industry, their revenue is coming, the profits are coming from a certain sector, and the shareholders are saying, you got to shift. So they have to continue their businesses, and at the same time, they have to think, how do we pivot? And no one really has the answer today. Okay, that's the world we're living in. So what do you do? Well, since you're in the Bay Area, I got to tell you something. That you look for strategies, and one of the best strategies I can tell you is what happened in the Bay Area. You need a Steph Curry. And those of you who don't know Steph Curry, let me tell you that find out who he is. Because in the Bay Area, you need to know him. And this is where, by the way, his point shots, his percentage, and the number of shots he takes and the percentage of winning. And he's not perfect, but he's pretty close to it. But you can see gaps out there. But in that, you add Kevin Durant, and suddenly you find this map to be changing a bit, and you add Klay Thompson, and you keep adding, and suddenly you find that this thing is filling up, okay? So what's the strategy? The number one thing, which we saw a little bit earlier, you need talent, okay? You need talent, and this is from our experience. Some of us were there in RPE, our experience in RPE. The number one thing, you need talent. The number two thing, you gotta nurture the team of talent. It's very important, the environment that you create for nurturing. Because talent, if it goes in different directions, can give you bad things. So you got to sort of harness that and direct them in a certain way. How do you nurture is very important. Creating the right culture and environment is very important. Not enough attention is paid to this culture part, but absolutely, we are all human beings. And how you create the social part of it is as important as the technical part. In fact, you may not get the technical side if you don't have the social side as well. Creating opportunities for multiple shots at the basket. And that's very important. I mean, you can't win it with one basket. You got to take multiple shots because not all of them are going to win. So portfolio of approaches, we have some simple layups, but you also have some unbelievable three-pointers. You got to take that. And so this combination of a portfolio is very important. And that's, in fact, from our experience in RPE. What did we look for? We'll look for things like this. And I'll give you an example that many of my colleagues take, that if you look at the technologies that were developed, this is the horse carriage. We then created automobiles. And way before the automobiles became popular, there were many examples of automobiles that were tried out. Steam-powered, the Benz motor wagon, but these were very, very expensive. They didn't go anywhere. Until the Model T, in the manufacturing, someone talked about assembly line. Well, this is where it was invented. And it brought down the cost and improved the performance to the point that it was faster, better, cheaper than going on horses. And I think that's the key message, is that you got to try some shots at goal early on, and you may fail. That's okay. But amongst that, something will happen, and that is bring down the cost and performance, increasing performance, and you become disruptive to the industry. And this is a great example. These are pictures of New York City in 1900. And you can barely see an automobile. There's one red circle. That's the only automobile in 1900 New York City. That's 100,000 horses, 1,200 tons of manure per day, okay? 100,000 liters of urine per day. Talk about an environmental problem. Those are the heaps of manure, horse manure out there. This is 1900, and this is New York City in 1913, okay? In a matter of, and the Ford Model T was introduced in 1908. 5 years. Talk about disruption, and the horse business got disrupted, okay? And it's faster, better, and cleaner. It's cheaper, it's cleaner. And that's what happened. And there's some lessons learned out here. What actually led this to this amazing transformation? But it started long ago, and some of it may not look quite, what's the phone call? It's my daughter calling. So that's, you see this amazing transformation happen. So what are the different stages? And I think those of you who are interested, I'm so glad you're interested in nuclear, but you got to realize that a technology goes through various stages. We heard a little bit of that. Early stages, you need a portfolio. You need about a few $1 million, as we heard, for a few years. But as it progresses, you have a proof of concept, you have a proof of system. The proof of scalability is very important, because in energy business, if it doesn't scale in volume and size, it doesn't matter. And it costs more as you go downstream. Supply chain development, regulatory compliance, talk about regulatory compliance in nuclear, that costs money. And then, of course, product and services and the markets. And you may do the early stage at the university, but later stages, at least in the energy sector, the private sector has to come in. There are all kinds of tax policies. I won't even go through that, but that's the nature of business out here. And the question you're asking is often, it takes 20 years to go from something at a university downstream to get really scaled up. The question is, can we shorten that in some way? Because the investors in the early stages from somewhere out here not going to wait for 20 years for the returns. So how do you shorten that? Very, very important. And this is what we think it's going to happen. This indeed has happened in the solar business. As you increase the scale, the cost has come down. The nuclear business has gone the other way. This is some data from France. It's gone the other way. And this trend has to shift. This has to change fundamentally because the learning rate is negative in the nuclear business. The question is, why is the learning rate negative? We did a report for Secretary Moniz end of last year. This is probably the last report we did as part of his advisory board. And we had a whole section of what controls learning rates. Because in South Korea, nuclear is going the other way. It's going the right way. So why is it that in South Korea it's going this way, in the United States and France and all is going the other way? And I'm not going to go through all this, but this is not one reason. It's a factor of like 10 reasons, 9 or 10 reasons that all come together. But going small modular is a good idea, and for a variety of reasons, but it has to be more than just small modular. But all the electricity, I mean, at the end of the day, nuclear has to connect with the electricity grid. So let me tell you what's going on in the grid, because that's very important. This is the vascular system of any modern economy. The grid that we have today started about 120 years ago, and the architecture, not the devices, but the architecture has remained the same. It's the architecture of Nikola Tesla and Thomas Edison. It's the Tesla-Edison paradigm, where you have centralized generation, long-distance high-voltage transmission to medium voltage distribution in our feeder lines, and then low voltage use in our homes. And there's only one-way power flow, and the generation always tracks the load, so you can turn on a light and some generator has to ramp up. And the only way to communicate at that time was frequency. And so if you turn on the load, the frequency goes down a little bit, and some operator in the generating station has to ramp it up to bring it back to 60 hertz or 50 hertz, or whatever that may be. And so that's been the paradigm that we're living in. But because of these drivers of change, and the drivers of change, as we talked about, is decarbonization. And so what are the options we have? Well, the options is to go to deep renewable penetration. California has decided to go more than 50%, 50% 2030, and now they're talking about 100% by 2045. Boy, that's going to be hard. And we really don't know how to get from here to there. And that's going to be, could be expensive as well. Nevertheless, renewables is one, demand side management, that's carbon capture and sequestration, or nuclear. We really don't have more choices than that. And the other driver that is changing in the electricity system is deep penetration, or increasing penetration of distributed resources, not just solar PV, but just contact points that are networked that you can control, like control thermostats, etc. But in terms of the top part, what are the options? Economics, because markets do play a role out here. What is the cheapest? This is what's going on. You have wind prices come down. These are contract prices. This is data from business, and it's approaching the point of about $20 a megawatt hour. Solar is also coming down, and there's headroom to bring down even further. What do these numbers relate to? Well, this is where US natural gas and China coal is, and this is where US coal and nuclear are. So these are the prices. Now, these are the long-term contract prices, but on a daily basis, how does it work? Can nuclear dispatch into the grid on a daily basis? Well, this is how the markets work, and I'll be very simple picture. Here's how the bidding that happens in a market goes according to a marginal cost. And because solar and wind have no fuel, the marginal cost is zero, essentially, close to zero. There's some operating cost, maintenance cost, etc., but close to zero. So they go bid lower, that's part of the demand, then natural gas goes, then nuclear, and then coal. And whenever the demand, the supply meets the demand, that's the price, and the rest of it is revenue. So you can go marginal cost really low. So the first thing that gets adopted is solar and wind, then natural gas, and if there's space for nuclear gets dispatched. If the load does not increase, okay, it's very hard for nuclear to compete today, except if you put a carbon price. If you put a price on carbon, this thing flips. And if it flips, then nuclear will go before natural gas. And that is why it is so important that if you have markets going on in wholesale, you can't not have a price and try to play in the market and try to decarbonize. It's trying to really run with your legs tied. Okay, so that's what's going on in the industry today. And unfortunately, nuclear is not making it in many places unless there are some subsidies or something. And frankly, there are subsidies for solar and wind as well. So this is a big deal because if nuclear does not dispatch, there's risk of shutting down, which is what was going on in New York and in Illinois till the state intervened in them. So this is a big challenge for nuclear, and I really hope that at some point we get a carbon price, and no matter what people say, coal ain't coming back because it's just too expensive. But because the renewables are getting integrated, because there are these mandates that we want to get 40%, 50% renewables, this is what goes on. The sun rises and it comes down. And because of that, you have what is called the duck curve. How many of you have heard of the duck curve? Well, everyone's heard, so I don't have to say anything. But there are some problems with the challenges that the duck curve offers with the grid, which the grid has never faced before. And that is because you have overgeneration during the day, and you have a massive ramp in the evening. So all the other things that if these things get bid and gets adopted the first shot, the other electricity generation services have to adapt to this. That's the world we're entering. It's not baseload power always that is important. It is ramps that is very important, and trying to load shift that is also very important. So load shifting, ramping are the new services that will have to get amplified in the wholesale market in the future, will get amplified. So if you look at the grid architecture where nuclear has to play, this is what is going on. This is what it used to be. You got the wholesale market and you got people bidding in, you got generation, transmission, substation, distribution, you got the homes. And you have a wholesale market, the utility, it's not really a market, but the prices are fixed by the utility commission. And this is monitored by the federal, in this United States, the federal regulators. This is monitored by the state regulators. And it comes to the meter and it stops. And what we're now trying to do is to inject huge amounts of solar and wind into the grid, which it was not designed for. It's volatile generation, not stable. And on the other end of the grid, you got volatility in one end, you got volatility at the other end as well. Because now you can control and turn up and down large amounts of loads on negative loads, which is generation, and they are all connected to the cloud in the computing world, and which means that you can collect the data, you can monitor, you can analyze, you can control, you can turn up and down large amount of loads, you can aggregate. And once you get aggregation, you can then sell those services into the wholesale market or to the utility retail market. So what is happening is that the wiring system of the grid is completely changing. It's getting rewired in a different way using information. That is what is happening, and it's going to happen even more and more. And of course, along with that, you get cyber threats that is happening. And it's unbelievable how many times, let's say PG&E gets pinged in a cyber threat on a daily basis. It's unbelievable. So looking at this grid, and this is where nuclear has to play. So we at Stanford looked at this and said, this needs some holistic approach, not just technical, but you got to bring the markets, you bring the policy, bring the regulatory side. And we created an initiative, launched it last year called Bits and Watts, which really looks at the holistic view of it. And of course, as the name suggests, bits and watts is very important because bits are going to be controlling the watts in the future. But coming back to the nuclear, let me just end with a few things and end with some of the observations that I just made in the previous session. The opportunities that nuclear provide are clear. The largest carbon-free source of electricity, we all know that. The largest carbon-free source of process heat, this is not appreciated enough. because process heat is going to be the most difficult thing to decarbonize in the future. I think we have options for electricity. It's very hard to find options for process heat in the future that you want to decarbonize. So this is going to be very important. We're on the way to small modular, which I think is a very good trend, because you can do the things that we just heard a few minutes ago. And believe it or not, I don't have to tell you, preaching to the choir, it's high safety. Okay? This is the advantage that we have. But there are some challenges. And challenges means opportunities. It is expensive. We saw the picture of Vogel plant, and the Vogel plant is going at about, $7 or $8 a watt? And whereas other sources that has to compete with are much cheaper, if you can get to baseload power of $3 a watt, that's going to be competitive. But we don't really know how to get there from the construction point of view in the current regulatory system. We heard about delays in construction. It is absolutely true, and you can look at the data not just in the United States, but worldwide. The time for regulatory approval and the process for regulatory approval, we are the gold standard in the Nuclear Regulatory Commission. This is the gold standard for the world. We think the UK is better. You go and talk to the UK people, they'll tell you the US is the one that is the gold standard. But boy, it needs some improvement in terms of the process. There's a question about waste management, and this inability to ramp, which I think is a myth, which can certainly be addressed. So all of these are challenges, but this is where, for the younger generation that is here, this is where the opportunity also is, because there's no reason, there's no law of physics that tells you the nuclear cannot be ramped. After all, we do that in our ships and submarines. So tell me a reason why nuclear cannot be ramped. There's a big debate going on, email traffic's going on about ramping, and I don't see at least any fundamental reason why it cannot be. And that would be one of the best things that can happen in nuclear. If in the mix of the grid we have volatile generation, if you can have the ramping capability, that really sort of jives with the new kind of nuclear that we can have. A lot of people say this is impossible. But let me remind you of some of the predictions that very famous people who are making now, but very famous people made in the past. These are called famous or infamous predictions of the past. This is Lord Kelvin in 1890. Radio has no future. X-rays will prove to be a hoax. Heavier than flying machines are impossible. Lord Kelvin was very opinionated. But he was dead wrong. But he was convincing to many, because he convinced Wilbur Wright that man will not fly for 50 years. Luckily, he had a brother, Orville Wright, who proved, and they jointly proved themselves wrong. One of the best quotes I have seen is by Arthur C. Clarke: any sufficiently advanced technology cannot be distinguished from magic. And it is really for us and all of you to do some magic. But let me end by what I just heard, by a quote from Margaret Mead. Never doubt that a small group of thoughtful, committed citizens can change the world. Indeed, it's the only thing that ever has. Thank you very much.